All right, great. So thanks everyone for coming. We're glad that you're here. We're excited to share more about our club, and we were glad to meet you over the previous few weeks through whatever venue it was. So this is the kickoff meeting for our spring semester, and so we'll be going over the background of our team, how we structure it, the sub-teams that compose the software, hardware, and operations fronts for our team, and then we'll finish up with some next steps that you can start getting involved. So with that, start off with some background. So why did we even start this club, and who is Wisconsin Autonomous? So first off, we think it's important to know why autonomous transportation and autonomous vehicles and robotics interesting in the first place. So there's a lot of expense and costs in transportation, shipping, services, many other industries across the world, and a lot of these operations can be made more efficient. They can be made safer. They can be made more easier for people to use. And so robotics and autonomous vehicles help provide a way to do that. And so together, these things can have a huge impact and a big wave in terms of making changes across many different industries. So with autonomous vehicles in particular, a lot of changes have been happening in the automotive industry, of course, where some major companies that you would think of like Ford and maybe Tesla, GM, are now starting to partner with some smaller companies that are focusing more on the software development of autonomous vehicles. So companies like Cruise or even Apple, that maybe wouldn't be immediately their own companies, are now partnering with larger companies and kind of creating this whole network of companies that are looking to revolutionize the transportation and autonomous vehicle industry. And so along with this, there's a lot of research and development that needs to go into making these cars safe for everyday use and to make them high performance enough so that people can trust them for consumer applications or for shipping things or just even in outer space. So that's where we come in. That's where Wisconsin Autonomous comes in. And the thing that we're trying to do is help research and develop autonomous cars. So before we get ahead of ourselves, we're going to do a quick little background on what autonomous cars are specifically, just to kind of get everyone up to speed a little bit so the rest of the presentation makes sense. So when a person's driving a car, you'd use your own eyes and brain to look around the road and see what's out there. You'd use your perception to see other cars, other pedestrians, the road lines, things like that. And for a robot or autonomous car that doesn't have a person driving, it uses other sensors. So these could be a LiDAR sensor, which we'll talk more about, or a stereo camera sensor, or other various types of sensors, including radar and ultrasonic, that we haven't used on our team yet, but will shortly. An advantage of autonomous cars in this area alone is that you can put sensors on different places of the vehicle and detect more than just what's in front of you on the road. So instead of being a person looking only straight forward, you can have full 360 vision, if you will, around the car. So already it can make the car more aware of its surroundings. So the second thing when you're driving is you might think about where you're going and what general route you're trying to follow. You might pull out Google Maps or use some other app so that you can help navigate which roads to turn on and which lanes to navigate through and things like that. So again, with the robot, it's not interpreting the environment in exactly the same way, but it's doing similar operation. This will be what we call state estimation, where it's forming a map using the sensors that it has of the surroundings. So being the obstacles, the roads that it can travel on, things like that. Next, if you're driving and you detect the environment and you also have a map of where you're going, then you also need to do the driving functions of knowing where to turn, how much to turn, and when to brake, things like that. This is a pretty intuitive process for everyday driving, you don't really give much thought to it. You just sort of turn the wheel and guide your car around wherever you're trying to go. But for an autonomous car, it's a little bit more complicated because we're trying to specify more precisely what input to give to the actuators on the vehicle. For example, instead of just saying to turn left, right, left, and straight again to get through some obstacles, you would have to say exactly what you want the sensors to do, what angles they want them to turn at, how much you want the car to speed up or slow down, and things like that. And then the whole system only works if it's running on a computer, of course. And so this is where it's important to have a well-developed software platform that's composed, of course, of computing hardware on the vehicle so that everything can run efficiently and process all the data that's coming into the autonomous car. So once all of that processing is done, then the car actually needs to go into motion, and that's where you need to think about the vehicle systems of what actuators are causing the car to increase the motor speed, and how the brakes are going to be applied, and how the steering is actually going to, how the front wheels are actually going to steer, and then all the mechanical and electrical systems that go into making such a system work in harmony. Now, with the whole, all the software and hardware things in consideration, none of it can be actually put together unless you have a good operations team that's working to supply the team with all of the experience, parts, money, and resources, and other planning tools that are necessary for keeping the whole process well-designed and on track, and cooperating well together with the different parts. And so together with these different systems, perception, state estimation, driving functions, the software platform, the vehicle system of the vehicle itself, and then the operations team, that's what takes us from like a human driving car to an autonomous car. And then we'll be going into more detail on each of these sub-teams do, but that's generally how the overall system works at a very high level. So Wisconsin Autonomous was founded fall 2018, 2.5 years ago now, with the purpose of advancing autonomous vehicle research and development. It has a pretty dynamic startup culture, and we work very fast on pretty flexible timelines to compete in national and actually international competitions. We'll get to that in a second. And so we do a lot of the designs ourselves. We're a pretty interdisciplinary team. We have a lot of people from a variety of backgrounds, from computer engineering to strictly mechanical design, and all the way back to just computer science software, and even, of course, the economics of our business team. We also have pretty well spread across different different age groups, and so you'll be sure to find somebody that's of a similar age and probably has had similar experiences in school on this team. And then, in addition to that, the team, along with several of the other automotive teams and other design teams, really reinforce a lot of the classroom skills that you learn on the theoretical side. So you can take a theoretical design and actually implement it, and the team has the resources to support whatever projects you're doing, and have a final result that you can test with, and like take pictures of, and learn at a deeper level how the theoretical concepts work. So these are some of the current sponsors that support our team. These sponsors support us through financial donations, through donating parts, through offering seminars to talk about some of our design plans and offer their experience. So it's really helpful to have these sponsors, and a lot of them are leaders in their respective fields. So competitions we're involved with. The first one is the EV Grand Prix, which is an autonomous go-kart competition. It's entering its third year as a competition, with the second year being canceled. So it's, for all practical purposes, the second year. It was canceled last year for COVID. But for that competition, we purchased a kit go-kart, and then have since converted it for autonomous driving and are developing the software for it. One of our goals this semester is to be testing that go-kart later this spring. We also were recently involved this past semester with the Indy Autonomous Challenge, which is is still currently going on, and was to race Indy Light vehicles at around 180 miles an hour on the Indy 500. The teams are developing the software only, and we collaborated with MSU for like first couple competitions before we decided to withdraw due to concerns with the amount of resources available that we had to contribute to commit to the competition, as well as some other logistical concerns. So we have since refocused our efforts on the SAE Auto Drive Challenge, which is more focused on urban driving than autonomous racing. So we think it'll give us some more diversity in terms of how we develop our perception, control, and other algorithms. And for that competition, we are given a full-size car from GM, and then we outfit it with the sensors it needs to drive autonomously through a fake course in Michigan. So the competition will last for 4 years. We'll also support several research projects. It's entering the second cycle. So there's a previous 3 or 4 year cycle that has now completed. And so now we are entering the second cycle of the competition. And so we'll be doing more preparation for that competition this semester as well. So here's a couple of videos just to demonstrate it. This is the example of one of the cars that ran in the EV Grand Prix the very first year. And so you can see like they took the driver's seat out, there's no driver there. And they've developed their own actuators for steering and like motor control and braking and things like that. So we have not the same, but similar setup for our go-kart. And I guess one thing that we're working to do that's different is we have remounted the components that we can fit the driver's seat still in the go-kart and drive it around manually to still collect data. This is an example of the Indy Autonomous Challenge that we wrote software for. This is in a simulation environment provided by ANSYS. And so for this one, it was to drive the fastest lap around the Indy 500 in the simulation environment. And so for this competition, we implemented what's called a pure pursuit algorithm, which you can learn about later. And it basically like allows the car to follow a previously planned path throughout the course. And then finally, this is a little preview of what's to come.
Just great seeing that progression.
So this is the Auto Drive Challenge, and these are just several different teams that have, as you can see, kind of their own sensor setups on the same stock car. We still will be working to develop all the software for this and like mount everything and test it ourselves. There being several years to this competition, there are like several stages. Next year will be mostly testing and simulation, but then the following year, then we get the car for the remaining 3 years to actually test with. So very exciting, and definitely like joining now will be the start of that competition. All right, so with that, we will move into the structure of our team, both as like on the organizational side, the tools we use, meetings, and some other information about those meetings. And then if you have any questions, I definitely encourage you to maybe like write them down or try to remember them and ask them at the end too. So I'm Alex. I'm the president of the team. And then we have our team structured into software, hardware, and business sections, where we have 2 software leads, Ian and Evan, who will introduce themselves in the slides to come, as well as a hardware lead, Jake, and operations lead, Julia. Julia, I believe, is here. So yeah, she'll also introduce herself. And then we have our remaining what we call sub-teams. So within the software team, to match those main autonomous driving components that we talked about, we have the perception team, software platform team, driving functions, state estimation team, led by Mason, Rudy, Richard in perception, and Raj in driving functions. And they can also introduce themselves as we go. The software platform team and the state estimation team are both looking for new leaders. So if you're interested in being a lead for this team, definitely stick around after the meeting. Come to the sub-team meetings and we can talk more from there. In the hardware team, we have the vehicle system sub-team led by Zach. Again, if you're interested in that team, with that sub-team and the other ones, we'll be going more in depth as we go. And then finally, for operations, there are open positions for marketing and finance, again, led by Julia, and we'll be talking about that one more as well. I guess just to point out, one advantage of our team right now is that since we are only like 2.5 years old, we are very flexible and have several leadership positions open, which maybe not, which is unique to our team compared to other teams that have like a more established, I guess, leadership structure and stuff like that. So just point that out. All right, so our team functions on a variety of resources, the first of which are Slack and Microsoft Teams. Sounds like everyone's familiar with, well, everyone in this call should be familiar with Microsoft Teams. Hopefully everyone's familiar with Slack too. And then we keep all of our documentation on Drive and our code in GitHub. We also have done project organization in the past with Trello and Gantt charts. Those are something that's more specified by the specific sub-team. So you'll learn more about how each sub-team structures their projects. All of this information has recently been condensed into a wiki page, which is fantastic. It's a great way of like organizing all the information that you're coming across right now. For example, we have a new member guide that we will send out a link for, and we have a QR code for, so that you can just follow some instructional pages to join the different groups that we're talking about and get familiar with the team. This wiki page also has some documentation on several different like technical resources that would be helpful to you going forward. So what does your involvement look like? We have 1 to 2 meetings a week. We have every other week all-team meeting that meets Monday nights at the same time that we are talking right now. And then there are several sub-teams that have a once-a-week meeting that spread out at separate times. So basically, like 1 week you would have an all-team meeting on Monday night, then your sub-team meeting, and the next week, no all-team meeting. We hope you take that time to finish your homework or do some extra work for the team or something, or just relax, I don't know. And then we have your other sub-team meeting that week as well. And again, these are all through Microsoft Teams, and then Slack is the main way that we communicate about those meetings happening or being canceled and whatnot. And then finally, with the all-team meetings, we have brown bags, or what we call brown bags, which are like short 15 to 20-minute tutorials on a select topic that someone is passionate about and wants to share with the rest of the team. All right, so with that, we're going to go into the sub-teams now. So let Mason talk more about perception.
Yeah, hi, I'm Mason. I'm one of the perception leads, and our weekly meeting is on Thursdays, 6:30 to 7 on Teams. So anyone who's interested can just stop on by this Thursday if they want. Yeah. So the purpose of perception for an autonomous vehicle is to recognize the car's surroundings. That mainly includes what and where. So like if you look at this picture below, it represents a pretty typical scenario that an autonomous vehicle would find itself in. And there's several key features that autonomous vehicles are for perception for an autonomous vehicle is interested in, and that's one, like the road. So figuring out, if you look at this picture, the autonomous vehicle would need to figure out where the road is, and you see that in the pink lines there. Those would be the 2 lanes for the road, and then also recognizing that there's an intersection right in front of the car, and again, there's 2 lanes. It'd have to be able to recognize that there's a left lane, and then also a lane to go straight, and then also along with the intersection would be detecting a stop sign, like yield signs, and then also the stoplight, whether it's red, yellow, or green, and then also super important would be figuring out where other vehicles are. So like in this picture, I highlighted one of them to use as an example. So like figuring out how far away it is. So in this case, about 10 meters. And then also its velocity. So about 30 miles an hour to the left would be important things to know about this image. And then also pedestrians, bikes, other um, smaller objects that you have to look out for when you're driving. So in this case, there's a pedestrian in the crosswalk about 5 meters in front of the car, and they're moving at 2 miles an hour to the right. Um, and then also, um, not only these like super common objects like vehicles, pedestrians um, need to be detected, but also it's super important that the vehicle can react to all types of situations it might encounter. And a very important aspect of that that's often overlooked is kind of edge cases. Um, so any features that might be in this environment that normally aren't present, but in very rare cases can be and are very important that the car recognizes. So in this image here, there's a railroad crossing on the other side of the intersection. And so it's super important that um, edge cases like this are picked up. Otherwise, you can obviously have some pretty bad outcomes. So yeah, and I guess along with the railroad crossing, like knowing how far away it is again, and then also recognizing um, whether or not there'd be a train um, coming. So yeah, so the goal of perception is just to kind of figure out exactly what's in the environment around the car, and then um, where those objects are. And then all that information gets passed on to the control systems. And those control systems are the things that actually try and um, decide what to do based off um, what perception is detecting in the environment. So then how perception would work for an autonomous vehicle. So it starts out with the real world environment. Um, and as it'll get talked about later in the presentation, um, the real world can also be substituted with a simulated environment in a simulation framework. Um, and so the sensors play the key role in turning the real world into digital data. And so then, um, I mean, typical sensors for an autonomous vehicle would be either LiDAR or camera, in some cases radar, ultrasonic sensors, other um, types of sensors are used as well. But for right now, we mainly focus on camera and LiDAR. So then on the slide there, the sensor on the top is a stereo camera. So it has two um, image sensors on it. Um, and then the advantage to a stereo camera over a regular camera is that using some um, clever tricks that are applied within the camera itself, it can calculate how far away each pixel is in the image. So like it can give you an XYZ position of each pixel in addition to the color. Um, and then you see the LiDAR that we have on the bottom. Um, and a LiDAR basically works just like radar does, um, except it uses infrared light instead. So how it works is it produces a laser that gets sent out and then reflects off an object in the environment and then bounces back into a sensor that then calculates how long it took for the laser to bounce back And then using the speed of light, you can calculate exactly how far away that point it was reflected off of is. And then the LiDAR basically does that millions of times per second in a bunch of different positions. And then it can basically um, turn the environment into like a 3D model um, based off that laser data, which you can kind of see um, a visual representation of that to the right. Um, so yeah, so once you have the visual data collected, so whether it be an image or a point cloud for a LiDAR, which is the um, name of what you'd call the visual data for a LiDAR, it's passed into a algorithm then, which can then make predictions off of what objects are in that data and where they are. So then on the bottom there, on the right, is basically just kind of the expected output you'd want from the computer vision algorithms. Basically just tells you, again, what objects are in the data and where they are. Okay, you can go to the next one then. So then progress we've made so far is the perception for the EV Grand Prix go-kart is finished. And that includes cone and vehicle detection using our stereo camera, and barrier detection using our LiDAR. And the barriers are just the um, boundaries for the course that the go-kart will be driving on. And then, ooh, and then active projects for this semester would include a LiDAR trial period, and that's with the new Luminar LiDAR that we'll be getting hopefully soonish. Um, Luminar is a fairly new LiDAR company they produce LiDAR equipment, and basically we'd be looking at purchasing one of their LiDARs, but they are willing to provide us with a trial period to kind of test out the LiDAR first before we make a purchase. And so kind of what we're aiming to collect, or what we're aiming to do with the LiDAR during the trial period, is to collect a bunch of data and then also explore any additional features that the LiDAR has. So that might include what this LiDAR can do that the current one we have right now cannot, and then figuring out what opportunities those additional features would open up for us, and then ultimately deciding whether this new and more expensive LiDAR is worth the cost. So then another kind of goal in the short term would be to replace our existing barrier detection, replace the current LiDAR we have for our existing barrier detection with this new LiDAR. And then the next goal for this semester would be designing a new object detection algorithm. And this would use some artificial intelligence and machine learning concepts. And this is something we're currently using off-the-shelf frameworks to accomplish. But moving forward, we're super interested in exploring creating our own, which would be the goal for this semester. And then along with that, using any of these machine learning algorithms, we would need to collect a bunch of data to train those algorithms on. And so basically once we collect both LiDAR data and images from the cameras, we'd have to label that data so that we can use it to train artificial intelligence networks for object detection. So that'd be another goal for us this semester. So here you can see a demo of the stereo camera running object detection. And this is driving on the RC car platform we have. And what it's doing is it's using the stereo camera to collect stereo images of this hallway and the cones, and then it's being passed into an algorithm that detects the cones in their position. So you can see the cones being highlighted and then their distance displayed above them. So yeah, this algorithm is able to differentiate like any different types of objects, and that includes color. So that way we can figure out whether it's a red or green cone, which helps for path planning purposes. So then this is our demo of our barrier detection. So you can see the lines on the left and right would represent the barrier course that the go-kart has to navigate. And this is using our LiDAR. So this is what the output from the LiDAR would look like, the point cloud. And that data is then being passed into a machine learning algorithm to identify the left barrier, which is the red points, and the green barrier, which is and the right barrier, which is the green points. And that basically then that information is passed on to the control systems.
Awesome. Yeah, and if you have any other questions for Mason after the meeting, definitely feel free to stick around. And then we'll try to keep the rest of these sub-team overviews to like a couple of minutes each, just to keep things moving along. So for state estimation, again, we're looking for new sub-team leaders. So if you're interested in a leadership opportunity, this is a great one here. Our meetings are, need to update that, Wednesdays at 5 to 6. So again, the purpose of state estimation is to estimate the vehicle state using the different sensors. This is for things like velocity, heading, acceleration, wheel slip, things like that. And then also map the surrounding obstacles and figure out kind of the surrounding obstacles and other important parts of the environment. Last semester, we made some progress working with the common filter and have some algorithms to map out obstacles into what's called an occupancy grid. And then our active projects this semester are going to be to implement our common filter into the ROS system that we use. More on that later to come. And then also finish mounting and testing some sensors and doing some other environment mapping. I guess what you see here, this is kind of an example of like what kind of an example of what we'd be working towards in the terms of the mapping environment. Not in the same sense of the Google Maps environment, but in the sense of mapping out the environment. This is an example of, well, these are examples of some common filter projects. So this is a little video of the occupancy grid so we're in the left and right boundaries that you saw Mason's LiDAR algorithm showing. This is just plotting it out into a map-like environment that we could plan around. And then similarly, this is a little simulation of a car driving through a figure 8. And then its position, velocity, and heading being estimated based on a model of the vehicle motion and also some noisy sensor measurements. So if you're interested in stuff with working with sensors and state estimation and kind of handling uncertainty, the state estimation team is a good one for you. All right, so with that, Raj, go ahead, or Evan.
Yeah, I just wanted to quickly introduce myself because I'm not going to have one of the presentations. But hi guys, I'm on the software lead. My name's Evan Deutsch. I'm currently leading driving functions with Raj. I was the previous lead, but he's kind of taking things over now and becoming the sole lead for himself. So I just wanted to quickly, before he goes, introduce myself. So everyone knows my face. So probably if you join driving functions, I'll be at all the meetings. Otherwise, I'll probably be around the meetings with Ian, who's also the software one of the software leads. But yeah, just wanted to introduce myself really quick. And yeah, nice to meet you, the new members.
Yeah, so I'm Raj. I'm the new driving functions lead. As Evan explains, like as he moves up into the software role, I'm going to be taking over. I guess we can get right into it. Could you? Yeah. Okay. So what we do in driving functions is we develop like control algorithms to race on a given track. So if you look at the in progress bullet points, is basically we work on path planning, path following, and obstacle avoidance. Those are like the three main categories of algorithms we work on. And in progress right now, we have two path planning algorithms we're working on. One is an optimal time path, and one is a strategy aware path. For path following, we're currently working on a Stanley controller. And then for obstacle avoidance, we're working on, we have two people working on an artificial potential field algorithm. And I know I kind of just threw a lot of crazy terms out there, but really all you need to be worried about is that path planning, path following, and obstacle avoidance are like our main current objectives. And I guess NPC also, that's something that me and Evan have been working on. And it's sort of like a local path planner slash follower. So what we're trying to work on this semester is get our algorithms working on a vehicle. So right now we have a couple algorithms that are finished or almost finished. So we want to kind of move on to the next step and try and get them working on an actual vehicle so we can test out how they run on the vehicle. Something else we're looking into is migrating current and past projects over to a new simulator that Aaron actually he was he previously worked on driving functions, but he created this new simulation environment for us, which is super intuitive. So we're moving our stuff over to the new simulation environment. And then also another just general goal for the team is we want to adopt a new Git workflow. So like Alex mentioned earlier, we use GitHub to sort of organize our projects and collaborate. So far the team hasn't really had a proper Git workflow, so that's something that we're looking into this semester. You can move on to the new slide. So this is an example of a simple PID, which is just basically a path follower. We have a little a track here with the red center line, and the vehicle is basically just following that path as it goes around. And then what we have here is a genetic algorithm that is used to plan a path for the vehicle. So you can see here, it's kind of a bunch of points along the track twitching around until they eventually settle on a set path. So it's going through sort of like these generations of paths and evolving slightly each generation to optimize for the shortest distance. And this is sort of what our goal is, getting it working on a working vehicle. So this is just a video of a RC car just driving around a path and navigating. Right now we don't have any of these our current algorithms on a vehicle, but that's hopefully something that we're gonna start getting working on this semester. All right then.
Okay, so as Evan mentioned, I'm the other software lead, and right now I'm operating as the interim leader for software platforms, which is the role I moved out of. So our weekly meetings this semester are going to be Wednesdays, 5:30 to 6 p.m., but that can always change. It doesn't work for people who want to come. So if you want to come and that doesn't work for you, just Slack us. We can work something out for sure. So broadly, what Software Platforms works on is the infrastructure for the vehicle. And as part of that, the ROS, the Robot Operating System, you don't need to know what it is. You'll learn all about it if you join, but it's basically how the different parts of our code talk to each other. Another big thing we do is vehicle telemetry, so we can monitor the vehicle while it's operating. It includes some sensor data that we can stream back to a computer, but also performance statistics like memory and CPU usage. We also work on the safety systems and software side of the safety systems to make sure that the car can stop when we need it to and it's not going to hit anything. And this is, for this semester in particular, one of our main goals is to make sure that the simulators we're using operate as similarly as possible to the vehicle. And so that means getting all of the interfaces we use to talk to the simulator to look the same as it does with the vehicle. That lets us make sure the code is portable, and that's going to be one of the main projects we're working on this semester. So this slide is just a diagram to give a broad overview of what the different parts of our software stack you've heard about tonight look like. On a technical level, all the arrows you see represent ROS topics, but more importantly, conceptually, they just represent the flow of information. So on the left, we have perception. They take in LiDAR data and camera data. They run their algorithms on it and get out some information about what they see. They give that to state estimation, who's getting like GPS data as well. So they can sort of create a map of the world around them. And then they give that to driving functions, who runs their algorithms for path planning and for actually like controlling the actuators to try to make the vehicle go where we need it to go. Then on the far right, we have the sort of hardware interface that talks to the motors we have for steering and also the braking system. And then also some sensors we have hooked up to those. So I just wanted to put this here to sort of give a big overview of what each of the different what each of the different subteams you've heard about so far, how they sort of operate together, and what that can look like when you put it all together. And so, as I mentioned, simulation is working on the simulators is one of our big goals this semester. First two I have listed here are really our primary objectives. The other two will follow on fairly quickly if we can get the first two done. But so it's making sure we can run all of our software in the simulators end to end without having to add sort of unrealistic sort of code in there to make things work. We need it to operate just like it would in the vehicle so that we can actually test it realistically. And as part of that is that second bullet point is to standardize the ROS interfaces. And what that actually means is important. If you want to work on it, or if you want to work on the simulations, you can learn all about that. But it's just making sure everything looks the same in the vehicle and the simulators. And so don't let this slide scare you either. Just sort of let it give you an idea of some of the technologies we'll be using to work on the simulators. So we'll be setting up the different environments, which can actually be a pain, which is part of the reason we want to make sort of virtual machine images or Docker containers for it. We're also going to try to write some tutorials and documentation to get ROS working with the simulators so that people throughout the team can get that up and running, hopefully as painlessly as possible. At the bottom, just some tools we use. So if you've worked with those, or if you want to work with those, you just want to learn them, it's a great opportunity to join and work on something. So this is just showing on the left is a simulation of a hallway environment that was made last semester, 2 semesters ago, I believe. And on the right is sort of a very similar environment. I think you saw this video previously. This just sort of shows what our sort of scale model simulations look like currently. this is a closer to sort of real life size simulation that was made several semesters ago. And this is just one of the simulation frameworks we're using. I don't remember exactly what the control algorithm here. I think it might just be a path follower, but this is what we're trying to get working for all of our sensor data to come from this simulation, and then for ultimately to also be able to control the vehicle in that simulation all together at once. And then this video you already saw, this is from the India Autonomous Challenge, but this was one of the simulation software they provided. We didn't do any work on developing the software. It's a commercial product, but this is just what it could look like. I think that's it.
Okay, great. So that wraps up the software subteams. And going into hardware, so Jake Borihan, who wasn't able to join us tonight, is the hardware lead. And then Zach Kluge, who also is unable to join tonight, is the sub-team leader for the vehicle systems team. Their meetings are Tuesdays from 5 to 5:30. So this sub-team handles everything that's mechanical and electrical on the car. It's a very hands-on team. It's kind of the more like raw implementation and testing of the systems that we're designing. It's everything from like machining parts and mounting things to the CAD modeling of the vehicle and testing to determine like the performance of the actuators and the go-kart in general. Some sample projects that are going on this semester would be to finish mounting some of the sensors, help with driving tests, model the actuators so that they can be used in our simulation environments, and then continue to improve the CAD model of the full vehicle. So some examples of what kind of the go-kart looks like. This is from this past summer. This is just an example of spinning up the motor remotely, and then also activating the steering at the same time. The go-kart looks reasonably different from this past video. It's had some significant mechanical upgrades, but just to give an example of what it looks like. And then this is kind of another sample project, working with some of the CAN software code. And then this specifically was just a brake test to make sure that the braking unit is properly clamping the brake disc. And with that, I'll pass it over to Julia for operations.
Okay, awesome. This will be fairly quick. You can go on to the next slide. Okay, first of all, a little bit of background about me. So my name is Julia. I'm actually a business student. I'm in finance. I'm doing investment banking this summer. If you're interested at all in like stocks or finance, a lot of the things you'll learn there is that it's about industry knowledge. And the wave of industry knowledge that's coming that you need to know is about automation. Specifically, self-driving cars is a really hot topic right now. And if you're thinking, well, I'm not a business student, I don't like stocks, that doesn't apply to me. Actually, a lot of engineers go back to get their MBA and then join management after a while in their career. So operations actually can be more relevant than you may expect. You can really see real application of business course concepts if you're a business student, which given this audience, you're probably not. But you can really bridge that gap between business and engineering and see what that's like, think in a different way, and that will help you later on in your career. Okay, so what we're looking for here is there's like mainly 3 parts to this area. There's marketing, which is the way that we get people's attention. Operations, which is where you're looking at sponsors, supply chain, like where we get our parts, budgeting, that sort of stuff, and team logistics, so like member acquisition events. And then finance is the more specific numbers game, so like budgeting, financial analysis, like how that budgeting is going, where we can spend more or less. And then, of course, relationships with sponsors, which is going to be one of our main focuses this semester. So if any of that sounds like something that you might be interested in, It's not a huge time commitment. It's actually, you can think of it more as something that you can add on to what you're doing to make yourself a stronger candidate for internship, for full-time positions. So just if you think these things would be good to know, if any of that describes you, send me a message on Slack once you get signed up. That time commitment honestly might be a bit higher than what we're working on right now. It's more about maybe 1 to 2, but the more people we have, the better. So yeah, I think that is, and this is basically what I've been talking about so far. So a lot of careers are all about networking. I'm sure you guys have heard the phrase, like, it's not what you know, but who you know. Engineering commonly tends to be both of those things. You really do need to know your stuff, but a lot of it comes down to just knowing the right people. In fact, my boyfriend was part of Formula on campus, which is like similar to autonomous, and he was really good at engineering, but he also met like recruiters at Tesla through being part of the club, and now works at SpaceX. And so similarly, those networking contacts you gain by being part of a club like this is what's really going to springboard your career after you graduate and for internships. Other than that, you have responsibility over your own projects. You really get to learn time management. You're working with that cutting edge technology like you are in your sub teams, but then you also get to apply that to what that looks like in the business world and what you might be doing later on if you do get an MBA or something like that. Okay. Yeah, there we go. That's it. So yeah, once you get a Slack set up, feel free to message me.
Great, thanks. And then yeah, just to reiterate too, in the Slack, there's a operations channel which you should have access to, that Julia has a lot of information through as well. So on that note, we'll talk about how you can get involved today. So first off, you can just scan this QR code or go to this link. That'll get you signed up onto our Slack channel. I believe most of you are, but if you're not, we can definitely help you with that. You should automatically be joining. It should automatically join you or sign you up for those channels. You can also join some of the other ones that we have that are not just the sub teams. We also use Teams. Everyone on here seems like should be familiar with it. So this shouldn't be a problem, but I guess if you have other friends, you can kind of invite them or let them know about this going through Teams as well. And hopefully everyone's able to find the meeting reasonably well. If you just use the link that was sent in Slack or over email or something, this might be important. Once you've joined the teams, like our Microsoft team, you should be able to navigate to the individual channel you want and then join whatever video call there happens to be. Just for this example, you go to the team, then the general channel, and then join the reading group channel, or the reading group call, or the all team call, or something like that. You can scan this QR code on your phone right now. This will point you just to the team wiki. We'll send this out on Slack later, but it'll help you get set up with whatever other steps you may need that you may or may not have done. And then the next step is just to attend the sub-team meetings throughout the week, depending on your own interest. And if you don't know which one, that's fine. We can help kind of direct you after the meeting as well, too. Joining the sub-team meetings is by no means a final commitment either. You can join as many as you like, or only one if you want. And you can definitely switch between them if you find that one is not what you thought it was, or if you decide that you want to experiment around. All right, so with that, what questions do you have? Thoughts, comments, concerns, and then I'll just leave this up as a reminder about those sub-team meeting times. Okay, so I know that we had one question here about what frameworks we should know to actively participate in the team. So my answer to that was, for now, just know Slack, Microsoft Teams, and eventually GitHub. If all you know is Slack and Teams, it's fine for now too. Our team, as you just learned about, uses several different software frameworks depending on the projects we're working on. Most of it is in Python and C++, and ROS is kind of a common glue for all of it. But again, that's something that you don't have to worry about for now, and that will get introduced in some more of the Subteam projects. And then last thing, I guess, again, if you haven't done so already, please join the Slack, join the team, the Microsoft Teams, and GitHub. You can view it by scanning this link, and then you can also go to the some of the other wiki page information. That'll be very helpful for getting set up. All right, so any other questions? All right, great. Well, thank you everyone for taking the time to come. We really appreciate it. We hope to see you at the Subteam meetings to come. And if you do have any questions in the meantime, please message any of us on Slack. Just send a message to the general channel, and we'll be sure to answer it as fast as we can. So thank you, and have a good rest of your night.